Welcome everyone. How are you? How are you doing? It's me, the pioneer is Mourad, Mourad Sultan Ezouidi. Good evening, everyone, and welcome. So my name, as you know, is Professor Mourad Sultan Ezouidi, and today I am very pleased to guide you through something truly exceptional: the exact symbolic solution of 12-degree polynomial equation using my method, Ezouidi theorem. Before we begin the calculation, it's essential to understand why classical methods, even the most famous ones, completely failed when trying to solve such high degree equation, such a high nth degree polynomial equation. I'm going first to start with asking a question: why classical methods fail? Let me explain clearly. Abel's theorem or Abel's impossibility theorem states that in general, polynomial of degree 5 or higher can't be solved by radical or can be solved exactly by radical. Galois theory also proves that the group of structure of such equations becomes too complicated for a radical solution. Approximate numerical methods, like Newton rupture, can only give approximate decimal roots, never exact symbolic expression or symbolic roots. Computer system often return approximations or leave the solution unsimplified. Factorization method fail because such polynomials are irreducible over the rationals. In short, all classical methods either give up, approximate, or only partially solve. They are not capable of producing exact simple fluids. This why, or that is why today we'll apply different approach. Ezouidi theorem, which open a new door. Here, I will share the screen my professors with you so that you can see the whole lecture. Okay, this one. Okay, share the screen. Yes, I shared. Okay, so we told that today's mission is to solve a 12-degree polynomial equation using Ezouidi theorem. Our goal here, or our target, is to solve this 12-degree polynomial equation exactly, with no guesswork or approximation. First, I will present the equation expressed in terms of the L subscript k minus 1 over the Q coefficients. The 12-degree polynomial equation in terms of Lk minus 1 over the Q terms, we consider the polynomial. We have P of x equal x raised to the power 12 plus L1 of order plus L0 of order x raised to the power 11 minus L2 of order q x raised to the power 10, like that. This is the coefficient. L0 is 24, L1 is 264, L2 is 1760, up to uh, L11 is 101. Here we'll use Ezouidi theorem. This is Ezouidi theorem. Is generalized for any n-degree polynomial equation. Just dive into the structure and substitute k with 0 up to 11 because the highest power of this 12-degree polynomial equation is in fact is 12. So 12 minus 1 here is going to be equal to 11. So professors and colleagues, teachers and mathematical researchers, you are going to use the Ezouidi theorem, this one, okay? And you'll apply. So this is our polynomial to the power 12. You see, we start from L minus 1, which is 1, the first coefficient of the terms, the x terms raised to the power 12, up to the x terms 101, x raised to the power 0, which is 1. Okay, and these are the coefficient of my polynomial to the power 12. Okay, here in fact I use my theorem and I solved this and I provided let's say symbolic roots, exact roots. Okay, we continue. We told that here. Okay, we told that these are the coefficients of my 12-degree polynomial equation. First of all, we are going to transforming to s subscript k minus 1 of order cube. Means I'm going to use the relationship between the original 12-degree polynomial equation to the new 12-degree polynomial equation that can be written as alpha subscript k equal L0 for the cube plus x subscript k divided by n. N is going to be 12, so I will proceed like this. Next, using Ezouidi theorem, transformation means I will use this theorem that I showed you before. Okay, I will use this theorem that I told you that I showed this before. Okay, let's go up. So this the theorem of the Professor Mourad Sultan Ezouidi helps you to find all the coefficients of this new 12-degree polynomial equation. Okay, then I will I will find the value of s subscript k minus 1. Means we convert the Lk of Lk minus 1 of all the two coefficient into the corresponding Sk minus 1 of all our terms, which greatly simplify the resolution. From the relation, or from the theorem of Mourad Sultan Ezouidi, this one that I showed you, this formula, okay, this formula comes here. We told that we found that the value of s minus 1 is 1. This is by convention. Like L minus 1 of 42 is 1, meaning the first coefficient of the x term raised to the power 12 is 1. S0 is equal to S1, equal to S2, equal to S3, equal to S4, equal 0. S5 here is different to 0. It will be 13,962,842 times 12 raised to the power 6. Then I should calculate, use the theorem of Mourad Sultan Ezouidi. This one that I showed you, I will use the theorem. Then I'm going to find S6 and S7 and S8 and S9 and S10 up to S11. Okay, just put K for it. To find the S6, put K equal 7. 7 minus 1 is 6. Then make the expansion and simplify this formula. To find the S8, you should put 9 minus 1. Okay, up to S11 means 12 minus 1. Okay, just use the theorem of Mourad Sultan Ezouidi, then everything will be clear for you. Okay. We told that we found the value of S6 is equal in fact to S7, equal to S8, equal to S9, and equal to S10. That's equal in fact to an hour. But S11 is going to be different to 0, which is equal to 800 minus 893,620,000, 25,000, and 883 times 12 raised to the power 12. Thus, the polynomial becomes in terms of s subscript k minus 1. Okay, so my polynomial has to be equal as that. P of x equal x raised to the power 12 plus s5 of 42 x raised to the power 6 plus s11 of all the r. So you can see this one, in fact, is a second degree polynomial equation. By setting y equal x raised to the power 6, will be y squared plus s5, y plus s1. I will use the decimal formula. Mourad Sultan Ezouidi when n equal to, means I will write my s1 of 42 dash equal minus s5 squared plus 4 times s11. Then I will find that the value of this discriminant, the s1 of 42 dash is negative. When, let's say, solving this, S1 of 42 dash has to be transferred on the right hand side. So it will be negative S1 of 42 dash. That's why we see here the S1 of 42 dash has been transferred and transferred transported without a negative sign. So here, or explicitly, P of x equal x raised to the power 12 plus 13,962,842 times 12 raised to the power 6 x raised to the power 6 minus 893,625,883 times 12 raised to the power 12. Let's explain the structure here. Now notes, only two terms matter. The x raised to the power 6 terms and the constant term, meaning this one and that, the last one. The structure is symmetric, meaning we can solve for x raised to the power 6 first, then deduce x directly. For example, if x raised to the power 6 equal a positive, for example, you write x subscript k equal a raised to the power 1 over 6 times exponential 2ki5 divided by 6. Okay, so meaning that the equation is reduced to the quadratic in x raised to the power 6. Now, my professors, colleagues, and mathematical researcher and learners, here the reduced equation is that. So x raised to the power 6 equal negative s1, s5 for the r plus negative root r minus s1 for the q dash divided by 2. Minus s1 for the q dash is equal to s5 squared minus 4 times s11. Substituting the values, we will obtain the following. So S1 in fact is equal to negative, S5 is equal to 13,960,842, but there is negative sign. That's why it's written here negative. Plus negative root of 13,962,842 times 12 raised to the power 6 all squared. We apply this minus 4 times times negative 893,625,883 times 12 raised to the power 12, all divided by 2. I will calculate this first. So this one has to be equal to 194 trillion 964 billion 531 million 220,496 times 12 raised to the power 12 divided by 2. You see this 12 raised to the power 12 raised to the power half, it will be 12 raised to the power 6. Then it remains only negative. You see this one I will divide by 2. And this number 194 trillion 964 billion 531 million 220,496, I should divide this by 4 to cancel the 2's in the denominator. So it will be like that. Okay, it will be x raised to the power 6 equal 12 raised to the power 6 between parentheses negative 6,981,421 plus negative 48 trillion 741 billion 132 million 805,124. This is the value of x raised to the power 6. Now I will try to find x and then final root alpha subscript k. Finding x. Now taking sixth root and adjusting by L042 equal 24. So alpha, so the exact roots are given by the formula x alpha subscript k equal L042, which is 24, plus xk, which is this. Okay, divide by 12, where xk is equal in fact to negative 6,981,421 plus negative root of 48,741 billion 132,805,124, all raised to the power 1 over 6 exponential 2k I5 divided by 6. Okay, then you see this minus 1, you can write as exponential I5. Okay, and this one comes up, minus down will be 5. This is no difference, will be remain no difference. Okay, so here the exact 12 roots are 6 roots corresponding to the alpha subscript k equal 2 because 24 divided by 12 is 2. Plus, you see this one, this 12 cube, let's say the sixth root of 12 raised to the power 6 is 12. So 12 here, 12 raised to the power 6, all raised to the power 1 over 6 will be only 12. That's why it has to be simplified by the denominator here down. Okay? Now I will write alpha k equal 2 plus 6,980,1,421 plus, I took the first positive number, plus root of 48 trillion 741 billion 132,805,144 raised to the power what? Raised to the power 1 over 6. Exponential to k plus 1 I pi divided by 6. Because this term was before negative. You see here, this one was negative. I will write negative sign. Okay, I will write minus 1 times this. So the sign of this change. When it was positive, it will become, when it was negative, it will become positive. So I will write as exponential I pi. Divide by 6, I will put it here. Same base exponential, I will add lambda c's. Okay. Here, this is for k equals 0, 1, 2, 3, and 4, and 5. Final conclusion here. In conclusion, also, there is another root. Yes, this one is the root. Alpha k equal 2 plus this one. Then and 6 roots corresponding to alpha k equal 2 plus this. You see minus and plus because of the discrete. Okay? And both of them are exponential to k plus 1 I divided by 6. Okay, you can see that all the roots are complex here, no real roots. I give this 12-degree problem equation to ChatGPT and he found 2 real roots. After giving him the solution and after checking, he told me he was sorry uh, when he wrote that there were 2 real roots. Okay, he made a mistake because here this is exponential times raised to the power to k plus 1 by I divided by 6. You can use Mourad theorem, will be cosine to k plus 1 b pi divided by 6 plus I sine to k plus 1 over 6 times pi. Okay, means all the roots in the first set are complex number. In the second set are complex number. Okay. So what else? Here, final conclusion. In conclusion, we have obtained the exact sample solutions of a very complicated 12-degree polynomial equation, completely beyond the reach of classical methods. This confirms that, or this confirms the extraordinary power of the Ezouidi theorem. Thank you all for your attention, and I hope the session shows you that the impossible becomes possible with the new thinking. Thank you for listening, and see you next time. This is the Professor Mourad Sultan. Okay, this is DeepSeek. Okay, look what DeepSeek wrote. I gave him the method. Okay, here. Look, after correcting it, I told him why you wrote, let's say you have 2 roots. So he addressed the answer. Look what he said now. He made confusion. Of course, he using method. No, this is my method. This is my method. I gave him. He told that, okay, you see, two reloads, x plus negative 26.88. Okay, before he told that complex number. So he was confused. Thank you for listening. This is the Professor Mourad Sultan video was reviewed and I used by the point. How can you solve the to the power problem? Inshallah, within time, if I have time, I will start explaining and mastering the solution of 13-degree point equation. Okay, 13-degree point equation. Thank you for listening. See you next time. Bye bye.